Hi, welcome to EE 550 video recording of the lecture. Alright, so since I'm gonna be missing on the date that's shown here, the 6th of December, I'm recording this video for you guys to watch on your own time to cover for this class. Okay, so where were we? We were looking into continuous random variables in the book chapter 10. Okay, so maybe a quick summary. I can show you the previous lecture notes and remind you where we were. The last thing we did was the transformations and how the distribution of the transformed variable can be found using this formula here, as you can see. Okay, so now today I'm gonna start with mixed random variables. So that's our topic today. Mixed random variables. Okay. So when we say mixed, what we mean is a mix of discrete and continuous. Okay. Mix of discrete and continuous random variables. And let's start with an example where we can see how this is happening, how we can get a mix of discrete and continuous random variables. So let's consider this random experiment. You flip a coin, and then if you get a head, you get an X that is a Gaussian, standard Gaussian, and that has a probability of P, the heads. And the tail, if you get a tail, then you just set X equal to 0, and this is with probability 1 minus P. So now let's see. For now, let's P is equal to 1 over 2. Let's assume that. Okay, so in the end, you can see here, if P is equal to 1 over 2, there is a probability mass of 1 over 2 at X equal to 0. Okay, so notice that probability of X equal to 0 is equal to 1 over 2. So typically in a continuous random variable, single points have 0 probability, but here we get non-zero. Okay, and this is a perfectly legitimate experiment. Okay, then how can we find the P sub X of X, right? So the easiest way would be to go from the CDF. Okay, go from the cumulative distribution function, because it's common to both discrete and continuous. Okay, random variables. Okay, so what is the CDF going to be in this case? F sub X of X with definition probability of capital X less than or equal to little x. We can write this as probability X less than or X given heads, and then probability of heads, okay, plus probability of X less than or equal to X given tails times probability of tails. Okay, again using simple probability rules. That's what we are doing. And we know that this part is basically, the heads part is Gaussian, so what we get is 1 over 2 phi of X. Remember, phi of X was the CDF of a Gaussian. Okay, and 1 over 2, what about this part? So this part, there's a probability mass at X equal to 0, so we can see that this is actually U of X, the unit step function. And let me define it here if you don't remember it. So 1 if X greater than or 0, 0 if X is less than 0. So this is the unit step function. Okay, so with this definition we can easily see that this is equal to 1 over 2 ux plus phi of X. Okay, now if you attempt to plot this thing, what you get is something like this. And yeah, so you get here up to 1 over 4 here, and then there's a jump here of amount 1 over 2, so you jump from 1 over 4 to 3 over 4, and then continue with your CDF, so up to 1. Okay, so as you can see there's this jump here which is of amount 1 over 2 due to the point mass. Now we can obtain the PDF from the CDF by using the derivative, right? That's what we have shown last lecture. Okay, now but what is the derivative of the unit step function? It's not differentiable, right? When you think about the unit step function, it's not differentiable at t equal to 0, but as electrical engineers mostly, we are familiar with what the derivative of u of t is. That's the Dirac delta function. So if for those of you who don't know it, let's define it. Define delta of x as equal to d by dx u of x. So this is called the Dirac delta function. Okay, so when you have a point mass, you get a delta function at that point. And let's write down the properties of the delta function for those of you who haven't seen this. I'm gonna summarize the properties. So basically the Dirac delta function integrates to 1, and number 2, a to b integral delta t dt is gonna be also 1 if a and b is the range of a and b contains 0, because there's a point mass at 0, right? So that's actually how we show the delta function. Okay, so at 0 there's like an infinite jump. At other points it's equal to 0. Okay, so number 3 property, f of t0 is equal to integral minus infinity to infinity f of t delta t minus t0 dt. So this is sifting or sampling property, This is an important property of delta. So if you multiply an f function with this delta, you end up evaluating the f function at the value, okay, of where the delta is. So okay, so this is delta t. When you shift delta t, what happens is that you're shifting your delta to t0. Okay, so let me take a stop here, pause. Okay, next property of the delta function is that it's gonna be equal to 0 for t non-zero. Well, what happens at t equal to 0 is we can say it's equal to infinity, but that's not really appropriate. So what happens is that you get a point mass at t equal to 0, which is the area underneath is always 1, as you can see from the property number 2 here. The area underneath the delta function is always 1, and it has like a point mass. So in our so these are the properties of the delta t function. Going back to the example, in this case what happens is the p sub x of x is going to be 1 over 2 the Gaussian into the minus x squared over 2 plus 1 over 2 delta x. So here you can see that there's a, so if you plot this, what you can get is a Gaussian with area 1 over 2 and then a delta at t equal to 0 on top of the Gaussian, standard Gaussian. Okay, so this is how the plot would look like. Now notice that even for pure discrete x, we can still work with the delta function. Okay, note, even for discrete x, we can work with the PDF, the probability density function, even though in discrete random variables we usually work with the probability mass function, using the delta function, the point mass idea. So delta function. So how would you find the PDF for a discrete x? So given a probability mass function for a discrete x, so let's call this x of xi, we can get the PDF. We get the probability density function for the same variable x, which is equal to sum over I from for all possible values of I of the discrete random variable p sub x of xi times, now we need to put a delta function at each point mass, so x minus xi. So that's how we can convert a PMF to a PDF. For example, let's consider this Bernoulli PMF. Okay, so let's say for a Bernoulli random variable, p sub x of x is going to look like this. Okay, so this is with p and this is with 1 minus p. Now if you want to use this variable as a continuous random variable and talk about its PDF, probability density function, p sub x of x, now it's a continuous now. Now you need to convert each point mass into a delta function. So what we need is again p and 1 minus p, but with the delta. So here px of x is going to be p times delta x minus 1 plus 1 minus p times delta x. Okay, and we indicate the amount in front of the delta function by this parentheses. Okay, but yeah, is this necessary to do for a discrete random variable? No. So if you, however, if you're only working with discrete, okay, however, if only working with discrete random variables, just use the PMF and just use. But if you somehow need to mix them up for it, then you can combine everything under the PDF umbrella by making use of this delta function. Okay, so let's do another example with these mixed random variables. Alright, so let's consider a continuous random variable x, which is uniform between -1 and 1. So this is continuous. Okay, now let's consider y, which is given as equal to x if x is positive, okay, equal to 0 if x is negative. Okay, I can also write this as y equals maximum of x comma 0 if you want. That's the same thing. Okay, so now y is a mixed random variable. So y is a mixed random variable. Now, so how would the PDF of y look? So we can see that there's a point mass of a probability 1 over 2. I hope you can see that at y equal to 0. Okay, so maybe I should start with the px if you want, but yeah, okay, I can. Let's start with the PDF of PDF of x, p sub x of x, which looks like this. So it's from -1 to 1, and the magnitude must be 1 over 2 just to integrate to 1. Now when you look at y, the whole probability mass for x less than 0 is mapped into x equal to 0, right? So the whole weight here, the whole probability weight go to y equal to 0. So when you think about the PDF of y, it's easy to see that it's between 0 and 1, and it's exactly equal to 1 over 2, and then we get a delta function on top of this for y. So p sub y of y. So the delta function has a weight of 1 over 2 as well, because of the area underneath x less than 0. So that's the mixed random variable y's PDF. Okay, maybe another example we can do. So if you sort of clip, so here we are clipping the value of x in this example. When x is less than 0, we are just taking maximum between x and 0 or something. So we are just clipping. So another clipping example. So let's say x is Rayleigh distributed, and let's say the p sub x of x is equal to x e to the minus 1 over 2 x squared. Okay, and in this case we know the shape, but yeah, so y equals g of x is defined like this. Now again clipping. So x, if x is between 0 and x max, there's a maximum allowed value, and it's equal to x max if x is greater than x max. So this says that I'm gonna clip the value of x to x max. I'm not gonna allow anything larger than x max. And so how would this PDF look like? Let's first again plot the Rayleigh PDF. So Rayleigh PDF is a positive PDF. It looks like this. Now let's say this value is x max. Okay, now if you set everything above x max to x max, so this probability mass here will map into the point mass at x max. So if I have to plot the py now, so this is py of y, what happens is that you get a distribution like this, and at exactly point x max you get a delta function, and what is the value of this delta function? It's gonna be equal to the integral of x from x max to infinity. So here the amount, so this whole weight is mapped to a single point. Whole weight mapped to a point mass again. Okay, and so now let's write down the p sub y of y, because that was the requirement for the example. So y e to the minus 1 over 2 y squared if y is between 0 and x max, and the other part is gonna turn out to be x max square delta y minus x max. So this is the delta function located at x max. Okay, well, I'm not sure if it's okay to write it this way, but and 0 elsewhere. Okay, so I can write this as p sub y of y equals y e to the minus 1 over 2 y squared u of y minus x max. So this is for the part between 0 and x max, plus the delta function, which is e to the minus 1 over 2 x max squared delta y minus x max. Okay, so you can see the details in the book how to find this. You just need to take the integral from x max to infinity. Okay, so this coefficient here is found by taking the integral. This is equal to the integral from x max to infinity of the Rayleigh distribution, which is x e to the minus 1 over 2 x squared dx. And to be able to take this integral, well, yeah, it's not that difficult, I guess. Yeah, you can take it. Okay, alright, so let's take a short break and then we'll continue. Okay, our topic now is how to generate continuous random variables. So in MATLAB, basically, let's say you want to generate continuous random variables. What can you do? Well, okay, we know we can generate a uniform random variable. Okay, we know we can generate a uniform random variable between 0 and 1. It's easy, and we just use the rand command in MATLAB that exists. Now the idea is transform this uniform random variable such that x equals g of u and p sub x of x is the desired PDF of x. But which function we should choose? Actually, we briefly talked about this when we were talking about discrete random variables. So the result is, I'm gonna just tell you the result or remind you the result. If you let capital X equals f sub x inverse of u, so f sub x is actually the CDF of x, okay, that you want to generate, okay. So you know what you want to generate, you know what the PDF is going to be, you know what the CDF is going to be. This is given this CDF function, if you directly transform u such that CDF inverse is used in the transform, what you get is an x that is distributed with the desired. X has the PDF p sub x of x, which is the derivative of f sub x of x. Okay, so that's the result. Well, you can say where's the proof or how to see that this works. Well, I'm not gonna give you maybe an official proof, but if you remember, also last time we talked about this, basically intuitively I think you can understand it this way. For example, consider, let's say you want to generate a PDF that looks like this, that has high values here. For example, this is your desired PDF. Okay, now what would be the corresponding CDF? The corresponding CDF will have a jump at the points where you have high probability, then it will be flat after that, right? So this is your corresponding f sub x. Now if you generate, okay, so this is 1, okay, so it goes up to 1, 0 and 1. If you generate a uniform random variable between 0 and 1, so this is your u values, and put the value here, for example, u0 is one of the uniform variables that you generate, and if you look back where it goes into the fx, from fx inverse where it goes, you get this x0. So let's say you generate a u1 and see where it goes back, x1, and let's say I'm generating a u2 and see where it's going back, it goes to x2, and this is u2. Okay, and then maybe I generate a u3 and this goes back to here. So as you can see, intuitively, what's happening is that these points are concentrated more where the PDF is high. So this is exactly what you want. So you want to generate more points where the PDF is high. So when you perform fx inverse u, that's exactly what you are doing. Okay, so this is really good. So you can intuitively see that this works. Okay, in general. Alright, so let's see how we can generate, for example, an exponential random variable. So generate x with a PDF p sub x of x equal to lambda e to the minus lambda x. This is the exponential random variable, and 0 for x negative. Now how to generate. First, generate your uniform, okay, between 0 and 1, and then find the CDF of x. Now find the CDF of x. We want to use the CDF inverse method, so f sub x of x is going to be the integral of the PDF, and it's going to be 1 minus e to the minus lambda x for x positive and 0 for x negative again. Alright, so what is fx inverse? F sub x inverse of u is going to be minus 1 over lambda logarithm 1 minus u. Okay, so that's the how do we obtain this? Basically we just say u equals 1 minus e to the minus lambda x, and then invert the function. Okay. So this is the function that we need to use. So generate a lot of uniform random variables, u1, u2, dot 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 un, from the random variable, uniform random variable between 0 and 1. So this means generate n numbers randomly between 0 and 1, and then convert each one with this f sub x inverse function, which is exactly minus 1 over lambda logarithm 1 minus ui, and then you obtain the corresponding x values, and then that's it. You're already generating your random variable realizations. Okay. Alright, so I hope this is clear. Sometimes it's not, there's no closed form expression for fx inverse, but don't worry about that one. You can do numerically and so on. So and if you can get a closed form expression, as we could get here, you can just directly use the closed form expression. I'm gonna mention a little bit about the real world example in chapter 10. Okay, for speech and audio acquisition, what you need is in a computer. So you want to acquire speech or audio in a computer. What you need is an A to D converter. So you get your x of t, and then you need an A to D converter, and then you will get an x of n. So this is actually digitizer, right? So you need to it both samples the signal and also quantizes. Okay, so it's quantizer and sampler. So but we will focus on the quantization part. So if you want to take the steps, x of t first goes through sampler, theoretically, of course. These are theoretical steps. and then a clipper is needed because for quantization you need to have your input between certain values, okay? And then so this clipper basically just clips the values of x of t between these maximum and minimum allowable ranges, and then you need to do the quantization, okay? And then you obtain x of n. Okay, well, and what is the clipper look like? Basically just the input to clipper is an x max value, which basically generates a y here, y of n, which is a function of the input g of x of n. Let me call this x hat of n, and let me call this x of n here. Okay, so this is x hat of n is the quantizer and quantizer output. Now basically what the clipper does is your values between, so the y is always between minus x max and x max, okay? So the y values become in this range. So what is the goal here? Of course we don't want to clip unnecessarily, right? So if we can determine what should be the clipped value, right? So this probability should be small. Of course we don't know what we are gonna get in terms of audio, but typically we can, let's say we can get a distribution for the audio that we will receive, and then we need to minimize this distribution having higher values than x max. And let's say I want to achieve this, I want to have this probability less than or equal to 0.01, so only less than 1%. So it's so that it will cause less distortion in the quantized thing. And we can assume that x is Laplacian. Assume x is Laplacian. This is a good assumption for audio signals. The distribution is Laplacian basically with the parameter sigma. And let's remind ourselves what the Laplacian PDF looked like. 1 over square root 2 sigma squared exponential minus square root 2 over sigma squared absolute x. Okay, well, we can by doing a lot of math, after that you obtain an x max value that is greater than or equal to sigma square over 2 log 1 divided by 0.01. So once you know the sigma is the variance, remember, you can obtain this x max value like that. So this is a practical thing that you can choose the clipping levels in your A to D converter using this PDF probability distribution. Of course you need to know what sigma is, okay? In your case you need to know what sigma is, and it is related to how big your signal is going to be, your input signal. Okay, so that's the end of the chapter 10 in the book, and I'm gonna stop here at this point. By the way, I think I'm gonna record only this part here, and then I will do the recording of the other part after I come back from the conference, because it's really, I have a little time left to go for the plane. Okay, so see you, bye bye.